All right, today we are tackling one of the most famous problems in all of mathematics, squaring the circle. I mean, for thousands of years, it's been the go-to example of an impossible task. But what if that's not the whole story? We're going to dive into some fascinating source material that challenges, well, pretty much everything we thought we knew about this ancient puzzle.
Okay, so let's set the stage with what we all think we know about the problem. It's this puzzle that stumped the greatest minds since ancient Greece. But the perspective we're looking at today kicks things off with let's just say, a very bold statement.
Wow, right? That is a huge claim. This doesn't just question the conclusion. It says flat out that the whole idea of it being impossible is false. So this one single provocative idea basically reframes the entire puzzle. But before we get into that, let's do a quick recap of what the puzzle actually is.
So here's the deal. You're given a circle. Your only tools are a compass and a straight edge. That's it. No rulers, no measuring allowed. The goal is to construct a square that has the exact same area as that circle. For centuries, this was like the holy grail of geometry, until, well, it was proven to be impossible. And the reason for that proof? It all comes down to one very, very special number.
And that number, of course, is pi. You see, back in the late 19th century, mathematicians proved that pi is a transcendental number. The simplest way to think about it is this. A compass and straight edge can only create lengths that solve certain simple kinds of algebraic equations. But pi doesn't play by those rules. You can't pin it down with one of those equations. So, a line of length pi just can't be constructed. The problem was officially impossible. Case closed, right? Well, maybe not.
Now, this is where it all gets really, really interesting. The argument we're exploring is that the mathematical proof, while it's totally correct, is actually focused on the wrong question. It asks us to step out of this perfect world of abstract ideas and into our physical, real one.
And here's the point, that proof of impossibility works perfectly in an imaginary world, a world of perfect points, perfect tools, and lines that have zero width. But the original Greek problem wasn't an abstract thought experiment. It was a problem of construction, a physical act. And you know what? In the physical world, the rules are just different.
In this slide, this is what it all boils down to. Abstract math lives in a fantasy land of perfect points and lines so thin they don't exist. But in the real world, you've got a real pencil. The graphite tip has width. Your compass point literally pokes a tiny hole in the paper. Nothing is perfect.
So this right here is the heart of the mathematical argument. Because pi is transcendental, you just can't construct a line of length pi with perfect, infinite accuracy using only those tools. You can get super, super close, infinitely close even, but you'll never be exactly there. And in the world of pure math, that's a deal breaker. But this is where our source poses a brilliant counter-question.
Just think about that for a second. In the real world, can you actually draw a line that is exactly 1 inch long? Not 1.00001, not 0.999999, but perfectly, infinitely 1? The argument here is no, you can't. And that idea, that changes everything.
And this leads us right to the core of the argument. This isn't a problem of mathematical impossibility, it's a problem of physical precision. The limits, it turns out, aren't in the numbers themselves. They're in our tools.
See, in the physical world we actually live in, every single measurement is just an approximation. Your accuracy is always limited by your tools and, frankly, by your ability to see what you're doing. And this leads to a pretty mind-bending conclusion. From a physical standpoint, the number 1 is just as imprecise or fuzzy to draw as the number pi. They're both trapped by the exact same physical constraints.
So if that's true, how would you actually go about drawing pi? Well, the author proposes a physical method. You take one of those infinite series from math that adds up to pi. You start adding the length of each term with your real-world compass, one after the other. And you just keep going until the next little piece you need to add is literally smaller than the mark your compass can even make. At that point, congratulations, you've drawn pi to the absolute maximum precision your tool allows.
And get this, the author actually calculates that to draw a line of length pi that's accurate to the width of a single atom, yeah, it'd be tedious. We're talking about 17 hours tedious, but it is physically doable. It's a chore, not some cosmic impossibility. But the analysis doesn't stop there. It actually suggests this whole focus on abstract, perfect precision might have been encouraged by the way the problem was framed in the first place. This leads to a really fascinating historical question. Why was the puzzle always about matching the area and not something else?
I mean, this is a fantastic question when you think about it.
It would be a totally valid geometric challenge to ask someone to make a square with the same perimeter as a circle. So why was it always about area? Well, this perspective speculates that maybe this wasn't an accident.
So here the source introduces a speculative idea it calls kinematic pi. I want you to imagine a taxi in a city like Manhattan, a city that can only travel on a grid of streets. Now, to trace a circular path around a city block, it has to travel along the four sides of a square. In that very specific context of grid-based motion, the author argues the ratio we call pi actually behaves as if it were the number 4.
So the speculation goes that by framing the original puzzle around static area, it might have, maybe unintentionally, steered thinkers away from even considering things like perimeter and motion. This, the author suggests, could have been a kind of historical misdirection that basically buried this kinematic way of seeing geometry for thousands of years.
And finally, the source uses this same focus on simple physical principles to give us a much more intuitive answer to another classic geometry question.
We all learned this fact in school, right? A circle is the most efficient shape for holding stuff. But why? The official explanations can get insanely complex, involving stuff like advanced calculus and theorems that are, let's be honest, pretty far from intuitive.
Okay, look at this comparison. On one side, you have all the jargon from typical explanations. Green's theorem, isoperimetric problem. It's a headache. And on the other side, the source's answer boils it all down to just two simple common-sense ideas. How far the edge is from the center, that's the radius, and the angle the edge makes with that radius.
And there it is, a simple, elegant, one-sentence explanation. A circle is perfect because at every single point on its edge, the perimeter is at a perfect 90-degree angle to its radius, and its radius is always the same. No other shape can do that, and that's exactly why it wins on area. Simple as that.
So, let's wrap this up. What's the big takeaway from all of this? Well, this analysis makes a really compelling case that squaring the circle is only impossible because of how we choose to define the problem. Sure, in the perfect, abstract world of pure math, it can't be done. But in the physical world, the one with real tools and real construction, it's not only possible, it's basically as possible as drawing a line of length 1.
And that leaves us with a final thought to chew on. Where exactly do we draw the line between a beautiful, abstract mathematical truth and a practical, physical reality? Maybe, just maybe, the impossibility of squaring the circle tells us less about circles and squares and more about the difference between our perfect ideas and the real world we live in.
Thanks so much for digging into this with us. We'll see you next time.